Now that we've talked about geometric series, I'd like to take a moment and tie this back into probability. So as an example to see the link here, suppose you flip a fair coin. Oops. Until it lands heads. We're going to let x be the random variable that counts the number of heads, or excuse me, not the number of heads, the number of flips this takes. So we're going to keep flipping the coin until we first see that it lands heads, and we're going to let x be the random variable that counts the number of flips until that happens. So a couple of things, we could evaluate the following. First of all, the probability that x is equal to 1. So the probability that x is equal to 1, that is saying that we flip the coin once and it lands heads. So that has a 1/2 chance of occurring. The probability that x is equal to 2, that's saying that we flip the coin once and it does not land heads. So just to be clear, the general structure. Of course, that's still 1/2, but just to emphasize, that's the idea that that first flip does not land heads and the second flip does. I'm multiplying there because I'm assuming that the coin flips are independent. The probability that x is equal to 3, we could see that the first 2 coin flips do not land heads, and then the third one does. And now I want to come up with a general expression for the probability that x is equal to k, where we assume that k is some positive whole number. So I can take advantage of what I've seen above. So notice that I have 1/2 times 1/2 times 1/2. I have 1/2 cubed. Here I have 1/2 squared. Of course, this could be written as 1/2 to the first power. So from the pattern I see, I have 1/2 to the k. Likewise, I could have thought of this as k minus 1 flips on which I did not see heads, multiplied by that probability that I do see heads on the kth turn. So we can do a couple things from our more recent knowledge. If I were to ask, what is the probability that x is less than or equal to 100? Now that I have a formula for the probability that x is equal to k, I can express this as a sum. So I can take the probability that x is equal to k and sum over the terms 1 to 100. In doing so, I would have then the sum from k equals 1 to 100 of 1/2 to the k. And importantly, notice that this is geometric. So we can take advantage of the sum formulas that we've developed. So the first term of this is 1/2 to the first power. And we have here that we're dividing by 1 minus our r value. R is 1/2. And in the numerator, we have 1 minus r raised to the number of terms. The number of terms is 100. So we could simplify this in that this multiplier cancels the denominator, and we would get 1/2, no, we would get 1 minus 1/2 raised to the 100th. So this geometric series there gives us a nice way to find a probability there. And then finally, if we were asked what's the probability, or what's the sum from k equals 1 to infinity of the probability that x is equal to k? From context, we know that this should be 1 because we talked about the sum over all possible outcomes, that the probability should be 1. But we can also verify this mathematically. So we can verify this now because the sum from k equals 1 to infinity of the probability that x is equal to k in this instance is the same thing as the sum from k equals 1 to infinity of 1/2 to the k. That's geometric. The r value in absolute value is less than 1, so that series converges. And moreover, it converges to the first term, 1/2, over 1 minus the r value. But this is 1/2 over 1/2, and we get 1. So now we have a way to actually mathematically justify that that sum is 1, where before we just knew from the context that it should equal 1. So to use it further, we can see it on an example where we can't intuit the value of the sum, so we can see where it's particularly helpful. In this instance, we're going to suppose you and another person are playing some kind of game, so a dice game. In this game, you take turns rolling a die. We'll assume it's a fair 6-sided die. And the first person to roll a 1 or a 2 wins. We'll suppose that you go first. With this, we can answer a few questions. A, what is the probability that you win on your first roll? So in this instance, again, we want to think about the fact that you go first. All we have to consider is just what's the probability that when you roll a die, you see a 1 or a 2. So this probability would be 2 out of 6 or 1/3. If we say now instead that we have the question here, what is the probability you win on your second roll? So we have to be a little bit careful here because there are some assumptions we can make from the description of the game. So to win on your second roll, that means that you could not have won on your first roll. We can assume that the game will stop as soon as somebody wins. So we have to first think about the fact that you would have to roll something not a 1 or a 2 on that first roll. And then we also have to consider that to get to your second roll, your opponent also has to lose their first turn. So that means they also must not have rolled a 1 or a 2. And then finally, on your second turn, you would roll a 1 or a 2. So just to be clear, this is you, this is them, and then you get to your second turn, you get this here. And I can start to generalize that. So if we say, what is the probability you win on instead your kth roll? Again, the assumption here is k is some positive whole number. So we've seen this for k equals 1, k equals 2, and now we want to generalize it. So I can think about this kind of grouping turns. So for you to win on your kth roll, you had to lose your first k minus 1 turns. Likewise, your friend had to lose their first k minus 1 turns. And then on your first turn, your kth turn, you won. So again, we're kind of separating this into the outcomes of what happened respectively for you and the other person. Notice that this general formula would hold. If k were equal to 2, we would get the result from B. And if k were equal to 1, we'd get the result from A. And then finally, this is all building up to allowing us to answer the question, what is the probability that you win the game? So notice the subtle difference in the way that this is posed. It's not saying on a particular term, but it's that you win the game at all. So the way to think about that is so if I were to give this some notation, let's let A sub k be the event that you win on your kth turn. Then the probability that you win is simply the sum from k equals 1 to infinity of the probability of ak. So it's the probability that you win on your first turn or your second or your third, etc. And in this case, again, we're thinking about or as addition. There's no overlap or intersection between those different events. So we're simply adding up those probabilities. Importantly, we can interpret our answer in part C as the probability of A sub k. So I can substitute that in there. So this is 2/3 k minus 1 times 2/3 k minus 1 times 1/3. And this, of course, looks like it is probably geometric, but we need to simplify it so that I can express it with one single r value raised to k in some sense. So to think about that, we have that this is the same thing as 2/3 times 2/3 raised to the k minus 1, all times 1/3. So this sum is equivalent to that of 1/3 times 4/9 raised to the k minus 1. And like we noted in the previous video, I could separate that as 4/9 to the k times 9/4. Or because I've gotten it down to k plus or minus a constant up there, I can actually jump right into my formula. Again, what I'm going to note is that the r value in absolute value is 4/9, which is less than 1. So this series is going to converge, and we can use our sum formula. The first term of this series is now going to be 1/3, because we would have 4/9 to the 0, which is 1. And we're dividing by 1 minus r. And we can simplify this a little bit. So that's 1/3 divided by 5/9. And if we take 1/3 and multiply by 9/5, then we're going to get 3/5. Automatically, since somebody would have to win eventually, we can deduce from this that the probability that you lose or the other person wins is 2/5. And it makes sense that the person who goes first in this context should be more likely to win the game. So this lecture, I just wanted to kind of make that connection back to, in some sense, why we started with probability, that it's related to series, and in particular, because geometric series are ones that we can actually find the sum of when they converge. Those make for some nice applications, especially in the context of probability here.